So welcome everyone to our NITheCS Seminar series. The reason we're going to keep is towards the end of the academic term, certainly in the teaching year. Now, it's been a great pleasure to introduce Professor Sarbari, Guha. I believe your maiden name was Weyl. Any question? So, Guha is from an institution in central Kolkata, and she finished a master's degree at Kolkata University. She got her degree and Department of Physics, and she completed her PhD from Kolkata University, but largely based in Kolkata.
Main supervisor from Kolkata University. The course provider was the
and then she went on to do a postdoc at Canada, which I didn't know working with the latest non-relativistic settles. Went back to Calcutta and eventually ended up at the university across the street, the central part of Calcutta, with Xavier's.
I mean, at university from 1991.
She didn't want the name. There's been
a job in Kolkata.
It's more than 20 years with illegal hands. It was built at a time when a very small as well as in France and Frankfurt. The research interests are in general relativity, and she was trying to describe research. She used the word effective adjective. That's uninteresting. It's uninteresting to use that adjective to describe the word. So, yeah. Oh, nothing. It's an unusual word used to someone who's so those of you who don't know, Sarbari is speaking back. She was his PhD from us. So over to you.
Yeah, and I think on that is really with market. I initiated into this and I did this nice introduction and so that's I won't spend much time and straight away go next. Gravitational entropy. We know that the concept of entropy is a very classical concept in physics and in thermodynamics, and thermodynamics actually revolves about entropy. So, and the second law is one of the most profound laws in physics. What's more interesting is that it is also applicable to cosmological spacetimes and to physical objects like black holes, wormholes, things like that, and to the universe as a whole. So we'll try to see how we apply this to the case of cosmology and astrophysical system. And this problem of gravitational entropy, the topic of my talk is today. So maybe there may be a bit repetition, but we know that the early universe was in a hot thermal equilibrium state, which is as expected to be a state of maximum entropy as per the concepts of thermodynamics. But with time, the entropy of the universe should increase. So how can that happen if the universe is already in a state of maximum entropy? So that was basically the question which led to the formulation of gravitational, of this term which we call gravitational entropy, which is basically the entropy of free gravitational fields. So let's begin our journey. Uh, so it seems that in presence of gravity, the second law of thermodynamics is violated because it states that entropy of the universe should increase. But if the universe is already in a state of maximum entropy, how can it increase? And so therefore, apparently, the second law is violated. But actually, it is not. So this part was addressed by Roger Penrose in 1977, and after his proposal of gravitational entropy, there has been several alternative definitions of gravitational entropy, purely geometrical construction, and recently, still 10 years back, relativistic construction of gravitational entropy based on relativistic thermodynamics. I'll come to that later on. Relativity and thermodynamics. This was actually initiated by Richard Case Tolman, and you can actually download his list of publication, and you will see how many papers he has published on this thermodynamics in relativity. And his book published, I think, by Dover publication, Relativity, Thermodynamics, and Cosmology. So it's a detailed book. So he was the first of this correlation between gravity and thermodynamics, but it was not exactly gravitational. But I actually acknowledge the work of Tolman before I proceed further. So yes. So this is quite short. Many things are written here. I will tell you, and I'll just concentrate on a few points. So slide. So what that this, as per Penrose's proposition, entropy, that is gravitational entropy, it reflects the degrees of freedom associated with free gravitational field. Before Penrose, there was Sakharov in 1967, who also proposed something like that based on the microscopic degrees of freedom. But that was not exactly the gravitational entropy. So here, in case of gravitational entropy, we talked about the gravitational degrees of freedom. Okay. But in Sakharov's proposition, it is the microscopic degrees of freedom, not the gravitational degrees of freedom. It's a slight difference. So the proposition of gravitational entropy provides a justification for the low entropy of the and this actually helped people to show that yes, the second law of thermodynamics is not exactly violated if we include the concept of gravitational entropy. And moreover, in this picture, black hole entropy appears as a particular case of the entropy of the gravitational field. I will not talk on that much, but this how black hole entropy emerges can be generated or constructed from the point of view of gravitational collapse was studied by Guha, Ellis, and I think there was someone else in 2015 in their PhD paper, but I will not speak of that in this. So, although it was Tolman who first formulated some laws of thermodynamics and relativity, but he was motivated by the work of Lenz, which was published in 1926, the paper entitled On the Equilibrium Between Radiation and Matter in Einstein's Closed Universe, but they were wrong with that formalism, which Lenz used for construction. The condition of equilibrium in the universe was assumed to be state of maximum entropy, but conditions which did not affect the total energy, but he was using the principles of ordinary thermodynamics in flat space. So it is difficult to find suitable expression for energy in case of curved spacetime, the proper prescription. This does not, straight away lead to a prescription in curved spacetime. So Tolman had to think in a slightly different way, but he was motivated by Lenz's work. So what he did, he considered two principles expressed in the form of equations. The first law that is constructed was the analog of the law of conservation of energy in general relativity. And so, but that was not so difficult to construct, but how to construct the second law. So what he did, he considered two principles. First of all, he said that the postulate must be expressible in a form valid in all quantum systems. And the second point was more stringent. That is, it must be equivalent to the ordinary second law of thermodynamics. So that's how he tried to construct the second law in his paper. So he introduced the definition of an entropy vector, which is given here, and dx mu ds is the macroscopic motion matter or energy. And this is exactly in the notation in Tolman's space. As a different proper energy density of entropy is measured by the flow observer. So that it obeyed a particular equation, that is the divergence of this entropy vector S mu integrated over 4 volume. So it included the universe as a whole should be positive or zero to that. Therefore, that is the entropy should be non-negative. Okay. I'll just skip over. Okay. Now, one thing, the correlation between connection between gravity and thermodynamics, and that became more evident from the laws of the theory of black hole thermodynamics. Now, there is a difference between black hole entropy and matter energy. So just quickly have a look at that. So in black hole thermodynamics, a black hole has a temperature, its surface gravity, and entropy proportional to its horizon area, and this temperature, entropy, and mass of the black hole satisfies the first law of thermodynamics. In fact, the 4 laws of black hole mechanics, but it's not that the 4 laws of ordinary thermodynamics straight away leads to the 4 laws of black hole mechanics. Instead, the 4 laws of black hole mechanics was devised in such a way that it can be correlated to the 4 laws of ordinary thermodynamics. So that this paper by Barden, Hawking, so that's the foundation in 1976. And that is still not gravitational entropy. This I've already mentioned. So, but there is a big difference. In case of black hole, entropy is proportional to its horizon area. In case of ordinary thermodynamic system, entropy is proportional to the volume. So that is a very important difference between black hole entropy and ordinary entropy. There's another feature, let me not mention and discuss it now because that's not my process, but still I included in the slide that the heat capacity of some black holes may be. Okay, so Sarbari's work I've already mentioned. Maybe I just move a bit further. Okay, so just like Sakharov, who considered this the space-time background as an infinite approximation of underlying degrees of freedom, but that was similar to the concept of continuum mechanics. Padmanabhan also worked on similar description of gravitational thermodynamics. So a few work. There are so many work. I mean, I can just go on, but two important work. One is because after Wittgenstein's work, which came up in 1995, Einstein's equation. So this was application in case of relativity. So he derived Einstein's equation from the book of the entropy and the RSM area, assuming that well-known relation that a Q equals TDS. Then in 1998, Xavier, he derived the unified law of thermodynamics and relativistic thermodynamics in relativistic spacetime. Subsequently, Pavlov formulated the first law on any horizon. From all these works, what was evident is that the second law of thermodynamics may be applied to a cosmological system. This is very important, and this development. So, if we assume that the universe is a closed system, there is a horizon, and we can think about what is happening on the planet.
Here's a question. The closed system, what you think of the universe is not a physical.
Okay. So this is the mathematics is quite consistent. If this assumption is imposed, then you can do the construction. Okay. Without this assumption, it's difficult to work. Now, these are a few mention of entropy functions which occur in relativity. One is black hole entropy. Then the entropy of cosmological horizons, the two are not the same. And then the gravitational entropy associated with the inhomogeneity. How it is associated with the inhomogeneity of gravitational fields, that we'll find out. So that was exactly Penrose's hypothesis, the Weyl curvature conjecture or Weyl curvature hypothesis. So that is number 3. And what is more important is that according to the generalized second law of thermodynamics, which is applicable to relativity, the sum of all these 3 entropies together with the entropy of matter, so usual thermal entropy of the universe, these 3 together with the usual thermal entropy of the universe, conventional entropy, that sum should always increase according to the generalized second law. So that is the point. So what is gravitational entropy and why should we consider it? Okay, this part is kind of repetition, so let me not discuss the same thing once again. But what happens is that the Weyl curvature hypothesis that Penrose proposed to solve the initial entropy problem, that the importance is that it provides a proper sequence to the occurrence of gravitational processes. So through this hypothesis, he said that there should be an entropy function which increases from the early universe to the later. And this entropy function is the function related to free gravitational field. So what is free gravity? Gravity means there should be some matter. No. Say you think of the vacuum outside a star where there is no matter. That vacuum will also possess entropy. So you can, because there is a gravitational field there, which is not interfered by some matter present in that region. So therefore, we can talk of free gravity and entropy of the free gravity. So this gravitational entropy is the entropy of that field. And it is measured by an entropy function, which we call the gravitational entropy function. So how to formulate that entropy function? Penrose said that it's the Weyl curvature tensor which should produce us a measure of this entropy of free gravity. But why? How? So let's see now. So we see the logic behind this proposal, that is Penrose's hypothesis. We know that the curvature of spacetime is given by the Riemann tensor, and it can be divided into two parts. One is the trace-free part, which is the Weyl tensor, and its trace is the Ricci tensor. Now, in the Einstein field equation, there is the Weyl tensor. It's the Ricci which enters the Einstein field equations. So, the Ricci tensor, in the Einstein field equations, we have the energy momentum tensor on one side. And so the Ricci is related to that matter energy momentum tensor through the field equations. So as the Ricci is related to the space energy tensor of matter fields in the Einstein equation, it should provide us with the information of matter. So who will provide us the information of the equation? So it should be provided by the that's so Penrose came up with this proposition of the Weyl curvature hypothesis and the inclusion of gravitational entropy solved the initial entropy problem. And you can have a number of slides on the initial entropy problem, but I have already mentioned the problem in a nutshell. So once again, I will, that was extempore, the way thoughts come to me. So I will just not concentrate on all the points because most of it is already discussed. I'll just mention one thing, that is the definition of what we call gravitational entropy was already there, which existed in the case of stationary black holes, and the paper was by Bardi, Parker, and Hawking, okay, in 1973, the same paper where we have the polars. But in the case of astrophysical black holes, not the stationary ones, which are being formed in a dynamic process, this concept of entropy was still not understood clearly, nor it was understood clearly in the case of a cosmological spacetime. So, especially in the case of cosmological spacetime, there is no universally acceptable and unique definition of gravitational entropy till then. There have been constructions, very successful constructions, but which are applicable to certain cases, not a universal definition till then. Okay, this part were already mentioned, so let me just the evolution of the universe is comparing to our expectation from the thermodynamic point of view. Because gravity naturally experiments, unlike ideal gas. So ideal gas spreads out and entropy increases. In case of evolution of the universe, it's attractive gravity which gives rise to density perturbation, local concentration of matter, structure formation. So we are having condensation instead of diffusion. So the concept of increase of entropy in case of a thermodynamic system like an ideal gas, and that in case of a gravitational system, these are not the same. Okay, let me not speak about it. So the initial entropy. The second one, the hypothesis about how the universe existed in the past. So this again, you can study about past hypothesis. So the second law and the past hypothesis make a low entropy prediction for the early universe, but we find that CMB itself indicates that initially the universe was in thermal and chemical equilibrium, so it must have been a state of maximum entropy. So there are in the next slide there are two figures. So it was difficult to accommodate the writing and the figure on the same slide because the figure was then getting condensed. So I split it into two parts. So I'll show you two figures. How the problem can be depicted in the first figure and how it is resolved in figure B, where we include the low gravitational entropy of a homogeneous matter in our universe and take into account a new maximum of entropy, that is gravitational entropy. So the total entropy is the sum of the gravitational entropy and the entropy of the initial universe, that is the CM. And moreover, we require for the total entropy to increase in course of time, the maximum of gravitational entropy should be greater than the maximum of the entropy of the microwave background. So that's how this problem of initial entropy was resolved. And this figure is due to Tolman and Weyl, who used this schematic to represent this problem. That is the maximum. I mean, it's just because the figure is not that, doesn't have that high resolution. So it's got split up. So this is the maximum entropy of the CMD. And this is the temperature of the CMD. It's an arbitrary scale. Temperature along the x-axis and entropy along the y-axis. So the predicted value is something lower than what is the observed value. So these two do not match. But the moment you take into account the total entropy, sum of the entropy of the CMD and the gravitational entropy, then at the temperature of the CMD, both the observed value of entropy and the predicted value of entropy are the same. This difference is the problem. Okay, so this is a very good way of justification. Let's forget this part. So, as I mentioned that black hole entropy is a particular case of gravitational entropy. I'll just tell you that this differential Hawking entropy is very important because it is the thermodynamic general relativity, and this is basically the expression. So those who have studied, they know very well. Move into the so different kinds of black holes, spherically symmetric, short-shaped black hole. So we have the expression for the current, that is a rotating charge black hole, that is expression. And if we take away the charge, we take away the rotation, this angular momentum, then things become different. Okay, so the short-shaped one very important thing which you should remember is that the entropy of the short-shaped black hole is about 4 into 10^77 Joule per Kelvin. It is 20 orders of magnitude larger than the thermodynamic entropy of the sun. Short-shaped black hole is basically a black hole formed by stars of masses having mass like the sun, solar mass. Okay. So,
what is the mass of this black hole? Solar mass.
Solar mass. Okay. So the point is, therefore, black hole entropy is different from the entropy associated with the star from which the black hole has been formed. Okay. So in the process of the collapse, the entropy has increased. How can it increase? That's a big question. But once again, this contradiction between conventional entropy and gravitational entropy in a mathematic representation. This is gas diffusion, entropy increases. This is gravitational collapse or structure formation, entropy increases. So as more condensation takes place, entropy increases. In case of gas, there's a rarefication where entropy increases. Okay, let's move further. Not. Okay, in a nutshell. Yeah. The gravitational entropy is different from conventional entropy carried by free gravitational field. Increase of gravitational entropy means increasing local anisotropy because there is condensation. It must be non-negative, like entropy. So there is a symbol. Should increase from a low value to high value monotonically as structure formation takes place in the universe. The entropy of black holes is a limiting case of gravitational entropy. Concept of gravitational entropy can be extended to local galaxies, black holes. And when applied to the short-chain black holes, this gravitational entropy is a suffocating instead. Black hole entropy at any time slice is proportional to the surface area of the black hole. It is the two-dimensional intersection of the black hole horizon and the cosmic. So, through this definition, this one of black hole entropy, one can naturally develop black hole thermodynamics in both classical and semi-classical realms, but once again, that is not our consideration at this point. Okay, this also I have mentioned. So, as per Penrose's conjecture or hypothesis, that the Weyl tensor should be therefore the measure of gravity. And as this is the classical expression for the Weyl tensor, and you can see generation mathematical theory of black hole. You get this expression and several other units. So this is the Weyl tensor in n dimensions. So we can construct everything in. Okay. So the hypothesis, Weyl curvature, what does it mean first? Physically, what does it mean? It means that the gravitational degrees of freedom remain non-activated at the time. That's zero. The Weyl tensor is zero. So initial space-time singularities must be constrained to have a vanishing Weyl curvature. First, Weyl gives us the measure of tendency. Okay, so if it is homogeneous minus Weyl is zero. Okay. Whereas the final space-time singularities, like those which occur inside black holes, are unconstrained. After the Big Bang, evolution, and this is Penrose's conjecture, but the construction there has been several other constructions. So after the Big Bang, evolution of particles was close to the Feynman and and be consistent with the second law of thermodynamics. Okay. So now, because of the initial low entropy requirement, there's some constraints on the Weyl curvature. Some suitable dimensional less must be asymptotically zero, and therefore, when anyone tries to construct the gravitational entropy function, the person has to find out whatever he or she is doing, they have to find out or construct this scalar function which is asymptotically visible. So there are several constructions, and there may be even more in future. End with the CET proposal, before, which is the Clifton Ellis proposal that came in 2013, which was motivated by some physical criteria and relativistic thermodynamics. It was a very elegant description. So I will end with that. And actually, we have also worked on that. Also done some research on the application of that. So a few definitions of this gravitational entropy function, beginning from the initial one. I mean, when these prescriptions, people started constructing the gravitational entropy function. So this is a very early construction of the function of Boltzmann's constant back again, and then square root of h. C is the one. H is the determinant of the spatial part of the metric. And then the canonical definition, but this is not variation. So this is in terms of the ratio of two states. Then from the canonical definition, we can do an integration and find the total canonical entropy due to free gravity's expression. And we can, from here, we can do some other multiplication, square root of the determinant of the special metric, and get an expression of entropy, which is in accordance with the second law. Okay. Now, Xenovilla and also Bonilla together, they showed that the Bell-Robinson tensor is suitable to provide a measure of energy of gravitational field. But that was gravitational super-energy tensors, that paper. And the Bell-Robinson tensor is defined in terms of the Weyl tensor. So this is the expression. It's the Bell-Robinson tensor, and C is your, these are all the, and this is the Weyl tensor, and this is the dual of Weyl tensor. So this is the construction of the Bell-Robinson tensor, and this tensor gives a measure of the energy, super energy of the gravitational field. It's this VR tensor which was used by Clifton, Ellis, and Tavakol. Then after that, Haley and Ellis, they introduced a gravitational Epoch function. So here, this is the Epoch function. It's an integral from W with tau is for volume, but W is in terms of periodicity and the velocity of the so observer for velocity. So I'll put the expression for W later on when I write down the CET proposal. Okay. Before the Clifton-Ellis government proposal in 2008 came another proposal which by Rutjord et al. The paper appeared in Physical Scripture. And that proposal was phenomenological, or rather purely geometric construction, not motivated by relativistic thermodynamics, but it's very useful in case of astrophysical systems like black holes or even wormholes. So in this prescription, the Rutjord proposal, the entropy, this is the gravitational entropy. It's not thermodynamic of a black hole. It's given by this surface integral, and this psi is a vector field, which can be constructed. But P is a scalar. It's a ratio of the Weyl square to the Riemann square. This P square. So actually, P is square root of that quantity. So this psi is taken into account. So that's how this quantity is gives us a measure of gravitational entropy. So there, Weyl has to enter in the expressions, whichever way you construct, and then you have to show that yes, it is consistent with the requirements of gravitational entropy. So to find in this Rutjord proposal, which was extended by Romano et al. To find the gravitational entropy, we have to do calculation in space. So we have to consider the spatial metric and then find the infinite surface element in 3D. So I, J, 1, 2, 3 over there. And we find the entropy density using the divergence theorem. And now what we did two works actually on astrophysical systems, one on black holes, another work on wormholes, where we use this Rutjord proposal. In the work on the paper on black holes, considered 4 cases. Accelerating black hole, accelerating, non-rotating, accelerating, rotating, charged, accelerating, non-rotating, and charged, accelerating, rotating. So 4 cases were discussed. I'll just show you one case which was dealt with in our paper published in, this was in 2021, I suppose, in IGNB. So we took the metric with all the parameters, and the singularities of this metric is also known. C is the deficiency factor, which is very important because it helps us to define the singularity. And we can calculate the total gravitational entropy at the outer, inner, and inner horizons as R plus minus. So this is graph plus minus. So there's a whole expression here. I'm just showing you the expression, final expression. And so for A equals 0, C equals area, and this here is the entropy. So if A is equal to 0, we get the non-rotating. From accelerating, rotating, we just get the non-rotating, and if the acceleration parameter vanishes, then we get the usual entropy for black holes, which was derived by Weyl et al. In 2012. And we can also get the entropy density. Maybe it's not just apparent. We have used small s to denote the entropy density and this is the total entropy density. So we can was behaving in the vicinity of the black hole. And I'll just show you one figure. So many other figures. One figure where the gravitational variation of gravitational is small, it's not bigger. For the accelerating rotating black hole, the variation with respect to this radial coordinate r and angular coordinate theta. This is really plot, and this is the density of this direction. So we chose certain values for which we got a good plot. So we find that for I equal to 0 and 0 equal to pi by 2, which is not a singularity, central function which is should happen. Finally, finish within 5 minutes. So, as I already mentioned, it is motivated by the consideration of thermodynamics and physical requirements. So those are all here. Let me not go into that. And it should also reproduce Wittgenstein-Hawking entropy for Schwarzschild. It reproduces. Here, the entropy function, the G function, was based on the square root of the Weyl-Robinson. So why? Because the dimension of the Weyl-Robinson tensor is L to the power of -4 instead of L to the power of -2, which should be the case for the entropy of gravity. So therefore, the square root of the Weyl-Robinson tensor had to be constructed to propose the definition of gravitational entropy by Clifton-Lewis entropy. So the entire everything is discussed in very detail in their paper. Let me just quickly tell you, and then maybe arrange on points. So they employ the gravity electromagnetic properties of the Weyl tensor to express the gravitational entropy. So I was saying that this W function, this expression was used by Lake and Melville also. They did not do it in such an elaborate. And they did not use the Bell-Robbins. Okay. Now this CET proposal, this is for Petrov type D and Petrov type N, because their argument was that anything else in other kind of spacetimes be ultimately reduced to the Petrov type D and but this Bell-Robinson tensor, that's the Kitches, it is uniquely defined in general. Such a definition may not be available in other theories of gravity, and such constructions may not be. Some other construction may be involved. Okay, so this is completely generated. So this W is the super energy density, and EAB is a that's a energy so we can find out square root small TAB, which is related to the Bell-Robinson tensor, which is the construction. And the realization was that the VR tensor is a unique Maxwellian tensor which could be constructed from the Weyl tensor, which behaves as a super energy momentum tensor for gravitational fields. So these are the expression of the effective energy density of free gravity, the temperature. Temperature does not just thermal temperature, it's temperature of gravitational field, which has the dimension. Okay, and then finally, as I said, that we applied this proposal to wormholes. So I'll just mention quickly one application we did, and we did it for the Alice wormhole also, but this exponential metric wormhole produces more elegant results. So just quickly mention. So this also, okay, this is also, and this is the metric Einstein tensor, and this was actually a counterpart with that anticipated. Construct the Hawk function, non-zero Weyl, gravitational energy density. Okay, and just temperature, quote unquote T graph, but that is not neutral to conventional temperature. Then find the many quantities, but this is an expression which can be plotted very easily. So get the variation of gravitational entropy along the gradient direction. So that is this, and we can also find the piecewise local gravitational entropy of the metric, and we get this is my last. So, and show that it is a good enough diagram, which is visible. 6 kind of wormholes were dealt with in that paper, where we used the Rudjot proposal as well as the CET proposal to determine the gravitational entropy. And Shamodjit wanted to do work for 12 wormholes. I said, leave aside the other wormholes. Let us
Questions?
Yeah. No, I was just
both
thinking
are
about
straight.
what,
Okay, straight.
So what is the physical concept of the steam graph? I'm trying to, I mean,
It's a matter.
beta.
No, see, it is a quantity which when constructed and put into the second law, everything falls into places. Number 2, it is arbitrary, it is ad hoc. It can be, I mentioned Alice wormhole, because the conventional expression for T graph as used in the field paper did not yield us a satisfactory value of T graph for the Alice wormhole. So then we found that, okay, they said that this is a bit ad hoc. So we made some acceptable change in the expression and got a very acceptable result. Right?
So this is more like a
Even
notion.
for mathematical.
Is a notion like Weyl.
Shobhit wants to say something because he did his PhD on.
This gravitational entropy. You can change the temperature function also. Okay. So that's one thing. Another is the integral is not completely arbitrary because it has it resembles that certain gravity.
Yeah.
Also. Then it
Fits
has
into that.
extra terms there. So we can reduce it to the blanket temperature, but that's a special case. Otherwise, it will act as a temperature function. So like that. So it's not actually the thermodynamic temperature that we
Yeah, that's what I
is the temperature that we associate the black hole with that.
Any other questions? While you're thinking about it, in your wormhole sort of application of the end, if I understand you correctly, when you get into the throat, the entropy decreases. Isn't that counterintuitive?
Yeah, it decreases, but then again, you can see on both sides. It's only at the throat. It's only at the throat it decreases, but otherwise on both sides.
People will change it. Anyway,
Because R equal to M is the throat, and we plotted for different values of M.
Maybe this is telling wormholes are thermodynamic.
Every formula.
We can continue with the questions, comments, and interactions over lunch. So let's plan the speaker again. Mary is very kindly arranged the slides. Surprise for us. What important to know there. So what happens is usually to lunch. So if you do not work, we do some lunch. Join us for lunch and we can talk about our focus.
And then I will reflect them to the direction of Samati.